Welcome to triple integrals in cylindrical coordinates. All right, so obviously that's what we're going to talk about in this recording. We define a box B in R3 in cylindrical coordinates by B is equal to R theta Z, where R is between A and B, theta is between alpha and beta, and Z is between C and D. As usual, we're going to divide each interval into L, M, and N subdivisions such that delta R is the quantity B minus A divided by L, delta theta is the quantity beta minus alpha divided by M, and delta Z is the quantity D minus C divided by N. Then for each box, B sub I JK, right, being R sub I minus 1 to R sub I, by theta sub j minus 1 to theta sub j, by z sub k minus 1 to z sub k, we're going to choose a point, think Riemann sum, as shown in figure 5.51 of the textbook, which is reproduced below. So since delta V, right, the volume of each one of these boxes is delta A times delta Z, where delta A, as we discussed when we were talking previously, is delta R times R delta theta is R delta theta. We'll define the triple integral in cylindrical coordinates as the limit is L, M, and N go to infinity, i.e., as those intervals get infinitesimally smaller of this quantity below, provided the limit exists, and of course that can be written as the triple integral you see there. If g of x, y, z is a continuous function on some, I say rectangular, but what I mean by rectangular is just a box. Here it's in cylindrical coordinates. B, again, written in cylindrical coordinates as the interval AB by the interval alpha beta by the interval CD. Then writing g of x, y, z is equal to g of r cosine theta or sine theta z, which we can represent as some function now that we'll call f of r theta z. We're going to have, and it's basically our usual definition, specifically is that we're going to have that the triple integral over b of my function g of x, y, z dv is going to be the integral from c to d, integral from alpha to beta, integral from a to b of f of r theta z r dr d theta. Okay. Of course, as usual, we can always change the order of integration to, for example, drop the dz, sorry. For example, dz dr d theta or d theta dz dr, you know, whatever happens to be the most convenient for the problem. So for example, if the region over which we need to integrate is a general solid, recall that we're just going to look at the projections onto the coordinate plane. So for example, given a general solid region E, where r and theta are in some the region D, and z is between two functions of r and theta, right? So D is going to be the projection of my region onto the r theta plane. We're going to have that our integral over E of my function f r dr d theta dz is going to be equal to the double integral over the region D times the integral over z with those limits of z as the limits of integration, f of r theta z. So we integrate with respect to z first, and then r dr d theta. And like before, we can talk about, you know, how the region D is defined. For example, if R is between two functions of theta and theta is between some constants, alpha and beta, then we can write our triple integral. R dr d theta dz. We can write our triple integral as the integral from alpha to beta, the integral from g sub 1 of theta to g sub 2 of theta, and then the integral of our functions u sub 1 of r theta to u sub 2 of r theta of our function f of r theta z, r dr dz d theta. And that's the idea. All right, so as usual, we should do some examples, or at least one. Let's evaluate the integral over the region E of y dv, where E is going to be the region that lies below the plane z equals x plus 2, above the xy plane, and between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. So first, we need to write the range for z, right? But we need to write it in polar coordinates, right? We need to change everything to cylindrical coordinates, and that actually makes sense here because we're integrating between two cylinders. All right, so since, what do we have? We have that we are above the xy plane, so z is greater than or equal to 0. And also we're below the plane z equals x plus 2, so z is greater than or equal to 0 and less than or equal to x plus 2. But now when we change to when we change to the cylindrical coordinates, right, we're changing x to its polar coordinate form, which would be r cosine theta plus 2. Now our region D is going to be the region when we project down onto those cylinders and we look at the projection on the xz plane, we end up with two circles. So now we're looking now into the r theta, but in the xy plane, we get the region between the two circles, x squared plus y squared equals 1, and x squared plus y squared equals 4. So the ranges from for r and theta are going to be what? So we get r squared equals 1. So that means r is 1 because r is positive. So r is going to be greater than or equal to 1. And when we look at the second circle, r is 2. So we get less than or equal to 2. And since they're both complete circles, theta is going to range between 0 and 2 pi. So we have, and we'll also change y to its equivalent form. So we're going to have the integral from 0 to 2 pi, the integral from 1 to 2, the integral from 0 to r cosine theta plus 2 of y we know as r sine theta, r dc, dr d theta. I could have chosen to do this any order that I wanted to. Well, not any order. I have to integrate z with respect to z first because z is a function of theta. But beyond that, I could have chosen any order. Okay, so here goes nothing. We are first going to integrate the inside. So r and theta are both constants. So I'm looking at the integral from 0 to 2 pi, the integral from 0 to 1 of z r squared sine theta, evaluated at those limits for z. Okay, so that's going to lead to the integral from 0 to 2 pi, the integral from 1 to 2. We're going to have an r cubed cosine theta sine theta. And that's going to be plus 2 r squared sine theta dr d theta. And so now we're going to integrate this bad boy with respect to r. It's going to give us the integral from 0 to 2 pi. And then we are going to get, in the interior, 1/4 r to the 4th cosine theta sine theta plus 2/3 r cubed sine theta, evaluating at the limits, and all. When we're done, we're going to integrate with respect to theta. Alrighty, so what is that going to give us? So when I plug in the limits, I'm going to end up with a 15/4 cosine theta sine theta plus 14/3 sine theta. And I'm going to integrate that with respect to theta. So there are a couple ways to do this. I could think about a u substitution on the to do the first half of the integral. Alternately, an easy way to do this is to rewrite this. We know that sine of 2 theta is 2 cos theta sine theta, or sine theta cos theta. So we can take cosine theta sine theta, and that's going to be 1/2 sine of 2 theta. So that gives us 15/8 sine of 2 theta plus 14/3 sine of theta d theta, which is how I thought of integrating it. And so now we take the antiderivative. We get negative 15/16 cosine 2 theta minus 14/3 cosine of theta. And we're going to evaluate that at our limits. And when you do all that work, you find out 0. All that work just to get 0. But we made it. So there you go. Okay, you should really pause the video at this point if you're, watching it for the first time, and kind of look through this again, make sure that everything's making sense, check my work, I'm only human. In the meanwhile, I'm going to carry on with the next example. Let us look at this problem. We just want to write this integral in cylindrical coordinates. We're not going to evaluate it this time. I trust that hopefully by this point you can evaluate integrals, and you should. And then you can always check your work in Wolfram Alpha or Maple or something, depending on what's functional at the moment, or what's the easiest for you to get your hands on. Alrighty, so let's write down what the limits are on our various variables. So what are our limits? We see that, okay, so the -2 to 2, that's on y. So y is between -2 and 2. X is between 0 and square root of 4 minus y squared, and z is between x squared plus y squared and the square root of x squared plus y squared. Okay, so these first two things, these define our region capital D. All right, so let's just look at that x thing. We know that x, let's look at the outer let's look at that boundary. X equals square root of 4 minus y squared. So one thing we can do to sort of see what's going on is just square both sides. And when we square both sides, what do we see? We see that x squared is equal to 4 minus y squared, or that gives us x squared plus y squared equals 4. Now, since x is greater than or equal to 0, and y is between -2 and 2, we see that our region capital D is the right half. It's the right half of the disk of radius 2 centered at the origin in the xy plane, of course. So in polar coordinates, what would that look like? Well, R is just going to be between 0 and 2, right? Because it's the whole thing. And what about theta? Well, there are a few different ways to define theta, but let's remember what's the picture that we should have in our heads is that this is my region D. So I need to go from down here to integrate, and I'm integrating counterclockwise. So theta would be from negative pi over 2 to pi over 2. If I were integrating clockwise, then I would probably choose then I might choose it a little differently. All right. Oh, z, right? We need our limits for z. Well, so let's rewrite the limits for the inequality for z. Word finding, it's so difficult sometimes. All right, so it's x squared plus y squared, that's just r squared, and then the square root of the quantity x squared plus y squared is r. So the integral then is going to become the integral from 0 to 2, the integral from minus pi over 2 to pi over 2, the integral from r squared to r of, and we were integrating x, y, z, so we have r cosine theta for x, r sine theta for y, and z for, well, z. And that's going to give me these, and don't forget that we have r from the dv part. So it's going to give me the r, and then I'm integrating with respect to z first, theta second, and r third, or simplifying that, I'm going to have, well, the limits don't change. That gives me an r cubed cosine theta, well, zr cubed cosine theta sine theta dz d theta dr. All right, so that concludes our fun with integration, triple integrals, of course, in cylindrical coordinates. Next time, we are going to discuss the even more entertaining integration in spherical coordinates. All right, have a great day and talk to you later.